For decades, telecommunications networks have operated on a two-dimensional premise: base stations deployed on the ground, serving devices on the ground. The next evolution of connectivity requires a three-dimensional coverage model. Achieving this required extending the standard protocols. Through 3GPP releases 17 and 18, spaceborne and aerial platforms are now officially integrated as core components of the 5G ecosystem. This reference architecture illustrates the distinct platforms required to build this network, relying on a combination of low Earth orbit satellites, geostationary satellites, and high-altitude drones. These vehicles act as relays, connecting diverse terrestrial nodes within a single architecture, linking maritime vessels, isolated rural coverage areas, and 5G mobile edge clouds. 3GPP specifies this integration as a required foundation for the 6G ecosystem, transitioning it from a rural backup option into the core network logic. Pushing data through the atmosphere to orbital platforms introduces latency, signal attenuation, and Doppler shifts that exceed the tolerances of ground-based network designs. The first engineering hurdle in orbit is bandwidth versus power constraints. A single wireless standard cannot simultaneously deliver gigabit broadband speeds and support low-power, battery-operated sensors from thousands of kilometers away. This table compares the parameters of the 3GPP solution, bifurcating the standard into two parallel, highly specialized baseband tracks. The first track is NR-NTN, built directly on the 5G new radio standard. It is optimized for enhanced mobile broadband and high-speed data transmission. The second track is IoT-NTN. This relies on the narrowband IoT standard and is optimized for delay-tolerant machine-type communication and massive sensor networks. While these tracks exist within the same broad standard, their physical layer parameters are incompatible. They require distinct hardware implementations on the silicon level. Regardless of the chosen baseband, dropping a signal over a 10,000-kilometer satellite link forces the protocol stack to exceed its designed timing thresholds. Terrestrial 5G relies on tight feedback loops. The protocol stack is engineered to operate within a strict 16-millisecond round-trip time. This chart maps orbital altitude against signal delay. At low Earth orbit, that 16-millisecond baseline stretches to 50 milliseconds. By the time we reach geostationary altitudes, the minimum round-trip time hits 600 milliseconds. This delay breaks the medium access control layer. The standard hybrid ARQ error correction protocol uses a buffer capped at 16 parallel processes. Over a high-latency satellite link, those 16 slots fill up waiting for acknowledgements, and the transmission process stalls. To prevent this, TS38.300 expands the maximum hybrid ARQ limit to 32 parallel processes. Alternatively, the network can disable this feedback loop, shifting error correction responsibility upward to the radio link control layer's acknowledged mode. Down at the physical layer, there is another adaptation. Because low Earth orbit constellations move at high velocities, the user equipment on the ground must calculate and apply Doppler precompensation to its transmission frequencies. Surviving the Earth-to-space link requires explicitly bypassing, extending, or modifying the synchronized control loops that make terrestrial 5G function. Beyond the protocol stack, the physical location of the hardware creates a technical bottleneck within the transparent architecture of releases 17 and 18. In transparent mode, the satellite acts as a passive RF repeater without baseband processing. Users transmit data up the user link, bouncing down the feeder link to a terrestrial gateway. Because the GNB resides on the ground, if this feeder link drops, the cell collapses. This creates secondary issues for the 5G core. As a passive satellite beam sweeps across thousands of kilometers of terrain, the access and mobility management function must manage moving cells and perform constant location verification. Treating a satellite as a passive mirror creates a reliance on terrestrial gateways, requiring the core infrastructure to process frequent and complex location updates. 3GPP Release 19 specifies a structural shift to solve this bottleneck. The network architecture transitions to regenerative payloads, introducing onboard processing. Under the regenerative model, the satellite ceases to be a mirror. The GNB base station hardware is lifted off the ground and physically hosted inside the satellite payload. To manage power and weight limits in orbit, engineers apply ORAN principles to execute a functional split across the Earth to space barrier. The distributed unit, the DU, remains inside the satellite, processing the physical and MAC layers locally and in real time. Meanwhile, the central unit, the CU, is kept on the terrestrial ground station. It manages the higher-level RRC and PDCP layers, reducing the computational load required in orbit. Placing the DU in orbit eliminates the feeder link bottleneck for real-time MAC decisions. This provides the network with operational autonomy in space, routing data without a constant round trip to the ground. Migrating the base station to orbit forces a structural change in the 5G core. Instead of routing traffic through the satellite, the core must now talk directly to it. 3GPP introduces a new radio access technology type, such as NRGO. When a connection is flagged with this RAT type, the core applies specific space-optimized rules to the data session. The mechanism enabling this synchronization is System Information Block 19, or SIB-19. SIB-19 broadcasts the exact orbital ephemeris data of the satellite. The user equipment receives this and calculates its own timing advance before attempting to transmit a signal. Finally, the mobility management function explicitly extends the non-access stratum timers. This prevents the core network from terminating sessions that are delayed by the physical distances of the link. By modifying the terrestrial protocol stack, adopting functional splits, and migrating base stations to orbit, the 3GPP has documented the technical requirements for a network that functions across 3 dimensions.